The next types of problems we'll talk about are known as bin packing problems. And the first kind of bin packing problem we'll do is a wood cutting application. And by wood cutting, what we mean is given a rectangular board of a certain length and certain information about which boards you need, how can you cut these up and how can you minimize the number of boards that you'll need. So let's look at this first example. So this first example, for a job you need, this right here means the number of boards you need. So this you need 5, and this is the length of the board you need. So you need 5 5-foot lengths. You need 2 4-foot pieces of wood, 3 3-foot pieces of wood, and 8 2-foot pieces of wood. And the store sells 8-foot boards. And given this, what's the minimum number of boards you must buy? Now, this question mathematically is actually quite difficult to solve. And in this type of application, we'll see we'll see one algorithm. There are a couple other algorithms you could look at, but for simplicity, we will assume that we can arrange what we need in a decreasing order. So this chart, for this example, I'm going to list what we need like this. So we need 5 5-foot pieces, 2 4-foot pieces, 3 3-foot pieces, and 8 2-foot pieces. These problems are generally solved by computers. In a computer, it might not be computationally quick enough to sort these and then go through an algorithm. So some of the assumptions on these algorithms are that you can't put them in order because it might not be worth the computing time to sort them. But we will assume for our examples that you can put them in order. And with that assumption, there's a very nice algorithm you can use that guarantees you'll be at least very close to the minimum number of boards. And what we're going to do is with this, just fill in boards as we can fill them in. And I like to do this with actual drawings of the boards. So our only restriction here is that these are 8-foot boards. So that's what our 8-foot board is going to look like. And let's start filling them in with the largest length. There are algorithms where you start with the smallest length. We'll do algorithms starting with the largest length. So first, we have 5 5-foot pieces. So here's one 5-foot piece. Now this is an 8-foot board, so you can't put another 5-foot piece up here. So for all of these 5-foot pieces, we're going to need boards like this. So for the 5-foot pieces, we need, so far, this many boards. Okay, now let's deal with the 4-foot pieces. All that's left on these boards are 3-foot pieces. So we can't put a 4-foot piece there. So we'll need a new board. And we'll put a 4-foot piece there. Well, now we have a second 4-foot piece. Well, what can we do with that second 4-foot piece? Well, we can't put it in any of these first 5 boards, but we can put it over here. And if we can fit it somewhere, we're not going to use a new board with this algorithm. So here, we're going to put that 4-foot piece there. Well, what do we have left? We have 3 3-foot pieces left. Well, we can use these boards. A 3-foot piece there, it fits there. A 3-foot piece fits there. And a 3-foot piece fits there. Well, now all we have left are 2-foot pieces. Well, we still have space here. We can fit a 2-foot there. There's only 1 foot left up here. We can't fit another 2-foot piece there. Similarly over here, we can't fit another 2-foot piece up here. Because this is 7 feet already used, so there's only 1 left. So with the boards we had, we were able to fit 2 2-foot pieces. But now we still have 6 other 2-foot pieces. Well, we need to put as many as we can on another board. They're not going to all fit on that board, so now we need another board. And we have another 2-foot piece and another 2-foot piece, not drawn to scale. So all of these are now accounted for. Now, one problem you see that could arise, well, let's answer the question. What's the minimum number of boards you must buy? Well, this algorithm shows we can do it with 8 boards. And now let's ask a second question. How much excess wood is there? How much excess wood? Well, I shaded in all the excess wood. There's a 1-foot hunk here, a 1-foot hunk here, and a 4-foot hunk there. So 6 total feet. 6 total feet of excess wood. Now, since these are 8-foot boards, this actually is the minimum number of boards we can use, given this number. Now, why is that? Well, let's say we went through this process and we had 10 feet in excess. Say we had a couple other boards that weren't used. And say we had an example where with 8-foot boards we went through this and had 10 feet in excess. Well, if we had 10 feet in excess, you might be able to rearrange the boards so that all of these 10 feet, well, so that 8 of those 10 feet wind up on its own board and you have one fewer board. But in this example, we had only 6 excess feet of wood, so we couldn't rearrange. We can't rearrange so that one fewer board is used. So in this case, we needed 8. Let's do another example. Now, fortunately for someone who's using a chalkboard or a whiteboard, this next example can be done by just changing one character. So the next example, instead of using 8-foot boards, we're going to assume the store sells only 7-foot boards. Now that's not standard. 8-foot is definitely more standard than 7-foot. But this is the example. So if the store sells 7-foot boards, well, let's follow the same algorithm. Let's assume these are in decreasing order. Here's a 7-foot board. There's a 5-foot piece. All we have left are 2 feet. That's not a 2, sorry. So we can't put any other 5s on these. Now, you might be tempted here. You might be tempted to just start filling in some 2s here. This algorithm we're doing, by putting them in decreasing order, will allow for that to happen. So right here, if you want, you can fill in these other 2s. So let's fill in all these 2s. They're all 2 feet, so let's use them up. We used 5 of them. There are still 3 left. For the rest of this algorithm, let's go back in order. So we have 4 and 4. 4. Remember, this is a 7-foot piece of wood. So if this is 4, all that's left is 3. So we can't put the other 4 there. So maybe I should make it go a little above half. And similarly, we have this other 4. Now, what's left? Well, we have 3 3s left. We can put one of them here. We can put one of them there. And we're left with 1 more. So we need another piece of wood to put a 3 on. And now, all we have left are 3 2s. So we can put 1 here, we can put 1 there, but now we need another board. So with this example, we need 9 boards, and we have 5 feet of excess. If we had, say, 14, or now let's say if we had 7 feet of excess wood, then you might suspect that you could rearrange the numbers so that all of the excess winds up on this. But we have less than 7 feet of wood, so this actually gives us a maximum. Now, let's look at another example. So for this example, we have this amount of wood that we need. We need 2 8-foot pieces, we need 2 7-foot pieces, and so on. 2 6-foot, 2 5-foot, 3 4-foot, 7 3-foot, and 2 2-foot pieces of wood. So let's do 3 different ones. Assume the store sells A. Let's assume they sell 10-foot boards. 10-foot boards. B. Let's assume they sell 9-foot boards. And C. Let's assume the store sells 8-foot boards. If they sell 2 different lengths of wood, this becomes very, very complicated. But assume the store sells that many. In each case, find the minimum. Well, I'm not going to say find the minimum, because the algorithm doesn't necessarily give the minimum. So let's say use the algorithm we're using is called the first fit algorithm. Well, I will say use the in each case. It's called the first fit algorithm because you put something in the bin it fits in first. In this case, you use the board that the piece will fit on first. So we want 10-foot, 9-foot, and 8-foot boards. I'm not going to formally define the first fit algorithm. I think that's easier to see with an example than it is to formally define it. So we have 10-foot boards first. Let's write these in order, because I like crossing them out as we go on. I find it helpful for organizing. So we have 2 8s, 2 7s, 2 6s, 2 5s, 3 4s, 7 3s, and 2 2s. And we want, for part A, 10-foot boards. Well, here's a 10-foot board. We're going to start with the largest. So we put an 8 there. We put an 8 there. Now we want to put 7s. We can't put 7s here, so we need a new board. 7. And the second 7 will go next to that. Now what about 6s? Well, 6s, all that's left on this is 2 feet. All that's left on this is 3 feet. So we can't fit a 6-foot board there. So we need another board for 6. Now what about 5? Well, that's length 4, that's length 3, that's length 2. So 5 needs a new board. But the second 5, you'll notice, we can put right up there. I'm actually going to change this problem slightly. I'm going to change this. I'm going to put a third 5 on it, so it's a little different than the first example in this case. So I'm changing this example for all 3 cases. I'm putting a third 5 there. So we used 2 of the 5s. The third 5, we would need a new board for, because the 5 isn't going to fit anywhere over here. Now what do we have? We have 4s. We have 3 4s. Where can they go? Well, they can't go here. They can't go here. One of them can go here. One of them can go here. And one of them can go here. Now you might think, well, let's use a new board instead of putting 4 here, because now we definitely have this one in excess because we don't have 1 foot boards. The algorithm we're using says to put it right there. It says do not create a new board unless you have to when you go in decreasing order. Next, 7 threes. Well, 2 of them can fit on those 7s. So these are 10-foot boards. 2 of them can go there. But now we need a new board for the rest of them. Well, 10-foot boards, all you can do is put 3 threes on one of them. And now we have 2 threes left. And we need another board for these 2 threes. Okay, that uses all the 3s. The 2s, fortunately, we can just throw them there. And now we have all of the numbers filled in. So how many boards did we use? And how much excess is there? How many boards did we use? 1, 2, 3, 4, 6, 10. So 10 boards. And how much in excess? Well, there's no excess here. 1, 1, 4. So 6 feet of excess wood. Let's do the next example. The next one says 9-foot boards. So let's use 9-foot boards. I'm again going to write 8, 8, 7, 7, 6, 6, 5, 5, 5. What is it? 4, 4, 4, 3, 3, 3, 3, 3, 3, 3, 2, 2. And in part B, we're going to use 9-foot boards. Well, again, we're going to start with the 8s. In these, once you have only 1 foot left and you don't have 1-foot boards, I'm just going to mark them off now as definitely not getting used. Just so I don't look at them and think I might have to consider them. Well, now let's put the 7-foot boards. Well, with the 7-foot, you have 2 feet left, and we could eventually use that. But let's follow the algorithm and go with the 6s next. The 6s can't fit on any of those first 4. They can fit there with 3 feet of excess. Now how about those 3 5s? Well, 5s aren't going to fit anywhere here. But we can create 3 new boards for them. Now how about these 3 4s? 4s can't go here because these are 9-foot boards. 4s can't go there because these are 9-foot boards, but all of the 4s can go there. Well, that's great. Now we have 3s left. 3s can't go here, but 2 of them can go there. And now we need new boards. I'm going to go, I guess I'll be able to fit them over here. Here's a new 9-foot board. 3, 3, 3. 3, or how many more 3s do we need? Let's cross off the ones we used. 2, and we used 3 more, and we have 2 left. And now we have 2 2s. They can go right there on top of the 7s using up those boards. So we have this much is used, and that much is excess. How many are used? 11 boards are used. And how much excess wood? 1 foot, 2 foot, 3 foot, 4 foot, 5 foot. Also known as 5 feet. Well, now let's look at part C, which says to do it with 8-foot boards. With these there are examples where you have so many numbers that it's very easy to overlook something. So when you're doing these, it's very tempting to jump over some steps, but I would recommend against that. The notes for my page, for what I prepared for this, if you see, they started off quite nice, and then they became very disorganized as I tried to do shortcuts. So I would recommend against using shortcuts, even if they seem like easy shortcuts, because I made several mistakes doing it, and I don't want you making mistakes. So here for part C, we have 8-foot boards. How many 8-foot boards do we need? Notice I haven't really been paying too much attention to drawing these boards to scale. These are 8-foot boards. Well, we need 2 of them to begin with. And how about for those next 7s? Well, we need new boards for them. And doing this, notice there are no 1-foot boards, so this piece is excess, and this piece is excess. Now what about these 6-foot boards? Well, we need new boards for them. So there are 2 6s. Now we have 3 5s. 5s can't fit there, so we need new boards for these. Well, okay. Now we have 3 4s. 4s can't fit on these. Remember, these are 8-foot boards. So we have 2 feet left here, and we have 3 feet left here. So we need to create 3 new boards for the 4-foot pieces. Do we? These are what? 8-foot boards. So put the first 4 here. What would the algorithm say is the spot for the next 4? Well, if it can fit anywhere here, then use that. It can't fit here, because this is 2 feet. It can't fit here, because that's 3 feet. But it can fit down here, because that's 4 feet. And then the last one also goes down there. Well, also goes on in the next board. Not also. The next 4 goes on a new board, because it can't fit anywhere. Now we have these 3s. Well, 3s can't go here. 3 can go here. A 3 can go here. And a 3 can go there. Well, that uses up 3 of them. But we also have these other 4 3s. One of them can go here, creating that 1-foot hunk that does not get used. Cross that out. We have 3 3s left. We have 8-foot boards. So a 3 and a 3. This is a 2 up here now. We can't put another 3 there. So we need to put the next 3 on a new board. And that uses up all of the 3s. And now we have just 2 2s. Those can go here. And now all of the numbers are used. So how many boards do we have? 1, 2, 3, 4, 6, 9, 13 boards. 13 boards used. How much excess wood? Well, look at all of this excess wood. 2-foot piece there. Look at this. This is a 5-foot piece not used. So we have 5 feet, plus 2 makes 7, plus 1 makes 8, plus 1 more makes 9, plus 1 more makes 10. 10 feet of excess wood in this case. So in this last example, you might wonder, is 13 optimal? Or could we rearrange this so that 8 feet of this excess wound up on the last board and all of it was used? Well, that is an interesting question. I would think the answer is no. But for now, we'll just say that this algorithm gave us this result with 10 feet of excess wood. Now let's look at another application of this bin packing. So here, a radio station allows advertising breaks of 120 seconds. The station has the following commercials with given lengths. It has a 100-second commercial, a 90-second commercial, actually two 90-second commercials, an 80-second commercial, a 50-second, a 60-second, two 50-second, two 40-second, two 30-second, and one 20-second advertisement. And we're going to use this algorithm to find the number of commercial breaks and the amount of dead air that would be forced to run. To run, I guess is probably the correct radio word. So this is another bin packing question. Here, our bins are 120-second time blocks. Well, before doing that, I'm going to write these all in order so I can cross them out. 100, 90, 90, 80, 60, 50, two 50s, two 40s, two 30s, and a 20. And here we have 120-second bins. So there's 120 seconds. Well, right here we have 100 seconds. So let's fill in 100. Well, the next one we have is 90. What's left up here is 30 seconds. So we need to put the next 90 in the next bin. Well, how about this 80? Well, that doesn't fit anywhere. So we need an 80 here. Notice here we have 40 seconds left there. I didn't mean to erase that. I meant to put an X through that. I guess I could be erasing them. Maybe that'd be easier. Now we have 60 seconds. Well, that doesn't fit anywhere, so it needs a new bin. Now we have two 50-second commercials. Well, this is a 20-second block. This is a 30-second block, 40-second block. This right here is a 60-second block. So we can fit that 50 up there. And we have a second 50, so we're going to need a new bin for the second 50. Well, now what do we have? We have two 40s. The first one, a 40 will fit in, that's why it's called first fit, is this 80. Because 80 plus 40 is 120. The next 40 will have to go over here, because that had 70 seconds left, and you could fit 40 seconds in there. Now we have these 30s. Where can we put 30s? Well, we can put 30 seconds in here, and we can put 30 seconds in there, because these are 120 seconds. And the last thing we have is this 20, which can go up here, filling that out, cross out the 20, and then we're going to mark off the dead air, since every number is filled in. And how many commercial breaks? We would need 6 commercial breaks. And how much dead air is there? 10 seconds plus another 30 seconds, with 40 seconds of dead air. Now, say you had a manager. Well, say you were in charge of determining the schedule for the advertisements. And say your manager walked up to you and said, "We're considering shifting to 100-second advertising breaks." So, the manager says, "We want 100-second breaks." And you have to analyze whether that is a good idea. So let's do that. So instead of 120-second blocks, we're going to use 100-second blocks. And let's see how this goes. Well, what do we have? We have 100, we have 90, we have another 90, we have an 80, we have a 60, we have a 50, we have two 50s, we have two 40s, we have two 30s, and we have a 20. But now we have, what, 100-second blocks. Well, this first 100 fills out its own block. And next we have 90s. They almost fill out the block. You can actually mark these off as dead air because this is a 10-second block and there are no 10-second commercials. Next we have an 80. These are 100 seconds, so we'll put the 80 there. Now we need a 60. Well, that needs its own block for this one. Now we have 50. Remember, these are 100-second blocks, so this is only a 40 left up here. So we can't use that for a 50, because that won't fit in. So for 50, we need a new block. Yeah, 50 is taller than 60 in these examples. Maybe I'll lower this and higher that. There. So there's the first 50. The other 50 can't go here, 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 but it can go in there. Now we have two 40s. Where can these two 40s go? Well, the two 40s, one of them can go here. The other would have to go in a new block. Now we have two 30s. Where can they go? Well, they can't go here because that's a 20. But they can go here, and they can go here. Or one can go there, and one can go there. And now you have this 20, which can go right there. So look at what happened with changing to 100-second commercial blocks. Now there are 7 commercial breaks, but with this scheduling, the only dead air you have is this 10 seconds and this 10 seconds. 20 seconds of total dead air. So this would be one of those good ideas that a manager has. Well, if you could use a 7th commercial break somehow. If you somehow can't absorb a 7th commercial break, then I guess the other one would be better. But this one, the previous one was what, 6 commercial breaks with, what was it, 40 or 50 or 60 seconds of dead air? This one has only 20 seconds of dead air. So this one could be argued to be a better choice.